Hi everyone. What I'm going to present is what we've been working on. What we've been working on at Willems, which is a zkVM for the MIPs architecture, and in particular for the OP for proofs from Optimism. So I'm going to dive into the implementation of the zkVM and the different choices that we made technically and the cryptographic component. So it's the same that I'm going to present in 3 days. So I'm sorry that I didn't have in your slide. It's going to be the same as zk social. So quick introduction. So I'm Willems from Willems. I'm a cryptography engineer there. So what's Willems? So Willems has been founded in 2019. So we incubated the MINA protocol and we continue developing it, but we do not focus only on MINA. So some of the introduction. So we still continue to develop MINA protocol, but we focus more broadly on research and development around zero-knowledge proof technologies. So to introduce very quickly the stack, so we've got different components in our stack that we use, and it's going to be related also to the zkVM. So we've got first Kimchi, which is a Rust library to prove the correct execution of programs. So it's strong-based, it has custom gates and also some lookup arguments. And also it's recursive friendly, and it's very modular also. Why it's important to mention that is because it helps us to integrate the work for Optimism, for the OP4 proofs. On top of that, we've got Pickles, which is our recursive layer. So it's the OCaml framework to write smart circuits as inductive rules. So we use Halo 2 as a protocol for the recursion. And on top of that, so that's more low level, but we want to bring also zkSnark to the web developers, and so we developed a library of framework in TypeScript, so which uses Kimchi and Pickles that helps web developer with a nice interface to write zkSnark in a web environment. So, and now what we are just adding is zkVM for the MIPs architecture, and in particular for Optimism for the OP stack. So yeah, I'm not sure if you mentioned that, but I'm gonna go through this anyway. So what's Optimism? It's for the zk dev. So, sorry. So it's I'm gonna go very quickly. It's a layer 2 scalability solution for Ethereum based on optimistic rollup, fully AVM compatible, and optimistic means that the state transition, therefore the transactions, are accepted without any verification. So the L2 state commitments are published on the L1, and there is a challenge window where the states can be refuted. There is the OP program, which is an implementation of the foolproof program that can be run in a MIPs VM that's called Canon to prove false in claims about the L2 state on the L1. Why I'm mentioning that is because we had already some ideas and maybe some code to write the zkVM, and Optimism came with this RFP to zkify, snarkify, let's say, the OP code proofs. So let's go into the one hat zkVM. A better name is coming. I have nothing else at the moment. So what's Rust code? What's the zkVM? One hat zkVM. So that's the joke that's on the website. I really love it, by the way, guys. So it's Rust code that we call Kimchi. That will be linked with OCaml code, because that will be compiled into WASM and JavaScript, or 1JS binding. That will have a TypeScript interface, or 1JS. I'm lying on these three for the zkVM. I'm not going to use that, but again, just for the joke. That's going to be originally Go code, so the MIPs VM. Arithmetizing a MIPS machine, so that's what I'm going to describe after. Running compiled Go code, so the OP program, and the OP program runs a part of the GEF code, so the Ethereum node, and that running compiled Go code that runs an EP. So yeah, that was just for the truth. So the MIPS architecture that we've got to support, it's a very specific one. So we've got 32 registers plus 2 other registers that I use for integer multiplication and division. So there is a memory of bit size of 4K. There is no floating point arithmetic to support at the moment. And external data can be read using system cores. So when we say the external data is the blocks, the L2 blocks that is used to as data to run the instruction have to run on some data, and it's done using the system cores. So I'm gonna describe the cryptographic choices that we made. So it's more specifically for cryptographer. I hope that it's okay. So the structure of the zkVM. So when you think about a VM, when you've got to arithmetize in a circuit, what you've got to do is to describe the instructions that are going to be executed. And therefore, a VM is just a transition from one state to another. So an initial state and a final state. So we first commit to the initial and the final state of the memory and the registers. And what's very important in the zkVM is how you're gonna read and write from the memory and the registers. So the instructions can read and write registers and memories. So in the zk world, we use what we call argument. So we use a variant of MV lookup, multivariate lookup on the trunk, that we call RAM lookup. So it's a work that we started before the RFP. How it works is we do a vector lookup on the memory index, the value, and also the last time that we read and write into the memory and the registers. Also, we do a range lookup on the last read and write index for history. And also multiple polynomials are used for the different lookups that we do. That is instruction. So one instruction is one row, and we can fetch multiple times the memory and the registers and read and write multiple times. So we represent that by using multiple polynomials. For the instructions, they're encoded as selectors in the circuit. And when we were implementing the zkVM, we needed a way to represent the internal state that an instruction uses. So an instruction is going to fetch some memory and some registers. It's going to perform some operations, and we've got to represent that in the zkVM. So for that we use a certain number of columns. It's 25 at the moment. Let's see if we increase or not. As optimism is compatible with Ethereum, is primarily developed for Ethereum, we have to have a way to be compatible with Ethereum, so we decided to use the polynomial commitment scheme KZG, and with the curve BN254. It was not the case initially in Kimchi, but thanks to the modular Kimchi library, the modular aspect of the Kimchi library, we could integrate it very quickly. quickly. When you've got a program, you can have very long execution trace, and we decided to use a folding scheme that is based on Nova, which consists of reducing each polynomial to a degree 2, because Nova only works on degree 2. And as far as we know, I don't know if it's recorded, but we think that it's the first Nova implementation with custom gate and lookup support. And as the Nova folding scheme requires a cycle of curve, we had to have another curve that is Gherkin. So we didn't find it. It's from Aztec, I think. And also, so the DOP program is gonna fetch some external data, and so we decided to implement also an integrity check. So to be sure that in the Canon implementation at the moment, when there is a pre-image key, the external data are not hashed to verify in the VM that the data corresponds to the hash that the program asked for. And so we decided to implement an optimized version of Ketchak, which uses a sparse representation of 16-bit for the booleans, and also the XOR operations operate on this 16 on the expansion. We expand on 64 bits, the 16-bit booleans. Also, I don't give the number at the moment, but we think it's also close to the state of the art, or even the state of the art in circuits. And it's done to read the external data using system calls. So that was a quick presentation of the different components of the zkVM. We don't want to stay. We don't want to only have this first POC for the zkVM for DOP stack. We think that we can tweak and optimize the current implementation, especially for folding. We had an offsite, and we had some ideas to improve the folding implementation. We want to also test with other programs than the OP stack. We also think about extending to other instruction set architecture. It's just ideas at the moment, not committing to anything. And we investigate also new research in the space of zkVM, and also MCC, which stands for Memory Consistent Check, which starts to be quite, let's say, trendy at the moment. So, for instance, George and Lasso, we had a deep look at the moment. So, yeah, that ends my presentation.
Amazing work.
Oh, thank you. We've got to chat after. I've got some questions. So.
How long is the proof gen?
How long is the
proof generation?
I don't know at the moment. I cannot give numbers, but we give numbers on the GitHub. I think it's 2 weeks or 3 weeks we give an update. Okay. I'm not responsible for that. Sorry, I cannot.
That's cool.
I cannot commit.
Sorry, I'm a little confused about the zk proof architecture. In the first few slides, you mentioned that you are using Halo 2, right? Mm-hmm. And then in the end, you mentioned Nova. So as far as I know, Nova is like complete replace. Like it's not a improvement to Halo 2. It's like replaces it, right?
It's totally
yeah. So which one is you're using?
So good question. Very good question. For the zkVM, we use Nova. I mentioned Halo 2 because it's our current stack. So it's the one we use for the Mina protocol, and it was the first version of the recursive layer.
And by Nova, you mentioned that you have custom gates and also, I think, lookup tables.
Correct.
Is by that, do you mean like supernova and hypernova, or you mean like your own thing?
I would like to read first the papers to say if it's equivalent or not.
Because in Supernova, their like main contribution was like having multiple like circuits in each step of the recursion, and in like Hypernova, they use like lookup tables. I think like is that the same thing or?
I would like to read
Yeah.
first to be sure that I can say only if it's the same. Sorry if I cannot answer. I don't have enough time. Yeah.
Just double checking. So you already have implementation of Nova integrated in Kimchi, like, or is it that you already?
No, it's integrated in Kimchi. There is a there
The
can be
same
PRs.
front end, I can choose to go with Nova or your
Yeah, so the interface is quite clean. So you just give, let me try to remember the interface, but you just give 2 instances and you can fold, and after it's going to be under, I don't remember the API, but it's going to be, we want to have something.
the implementation is there.
This in Kimchi, yes, correct, yeah. It is going to be.
Oh yeah.
But there is an initial PR called folding, so yeah.
So during the implementation, is there any incompatibility with the existing OP code or MIPs, or it's a fully?
So the first goal is to run the OP program. We're still dealing with some construction. So I don't think so. So, oh yeah, there was something that we would be nice to have is the C scores can only read and write 4 bytes at a time, which is a bit annoying because we've got a big amount of data with hundreds of bytes. So that would be nice. Yeah.
To explain the part, the fault-proof perspective. So you execute the fault-proof over a program. You want every instruction to be as small as possible, because the dissection only helps you reduce it to a single instruction. So the smaller the instruction, the better. Whereas with the zkproof, you have to running through all the instructions anyway. And so it's better to have less instructions that are larger than have many instructions that are small.
I spent a lot of time trying to.
I'm sure we can find some way to change it.
I was responsible for the C scores. So.
Quick question on the Ketchup implementation. So compared to Halo 2, like what sort of improvements have you seen with the sparse implementation of optimizing? Halo 2's implementation is always quite optimized for things, preparations and all applications. I'm just curious to see how the hashing is actually.
I don't get the link with Halo 2. I don't understand the link with Halo 2 application.
No, I know you used Halo 2 before. Like they have an optimized implementation of hashing as well out of the box. Not the system itself, like Halo 2.
Oh, the Halo 2 repository.
Yeah.
They've got a Ketchup implementation. I haven't benchmarked with it. I only check Aztec. But so we compare. We had a first check with Aztec, and because apparently they use also MV lookup, additive lookup argument, logarithmic derivative, how you want to call it. So we have to bench it. But first, we have a more efficient implementation. And we'll see the number. And it is open. I mean, you can always check the repository to be sure that we don't lie. So.